All right, welcome to The Explainer. Today we're going to talk about something kind of weird when it comes to software. The idea that the absolute best systems are the ones you don't even know are there. We're going to dig into some really smart thinking on how to build stuff that just, works. So let's kick things off with a big question, one that kind of flips a lot of tech thinking on its head. When you look at a really well-designed system, what does it actually look like? What do you see? Yep, that's it. Nothing. The best designs, the truly great ones, you don't even notice them. They're basically invisible. They're silent. They do their job quietly, perfectly, with zero drama. Okay, so let's really get into this. It's a bit of a weird idea, I know, but the true sign of a great system is that it's boring. Yeah, boring. Not flashy, not super complex, just stable. Rock solid. And this quote just nails it. You know how it is, right? We get so impressed by complexity, but we should probably be more suspicious of it. We see some crazy complicated diagram and our first thought is, whoa, that's some serious engineering. But really, the question we should be asking is, do we really need all that? And this really gets to the core of the whole thing. So on one side, you've got what I'd call the impressive system. This is the stuff that looks great on a resume, right? You're using distributed consensus, all these event-driven patterns, maybe some CQRS. It's complex, it's interesting. But then on the other side, you have a good system. And what does that look like? Underwhelming, simple, easy to understand. It's the kind of thing your team just says, yeah, it's fine, it just works. And here's the absolute kicker. You don't get to build the complex thing first. A complex system that works almost always, and I mean always, starts as a simple system that works. You have to earn that complexity. You can't just jump into it. Okay, so if simple is our goal, what's the big bad guy? What's the main thing we're fighting against? Well, it all boils down to one single concept. This is probably the hardest part of all of software, and that's state. Now, to really get why this is such a big deal, you gotta understand the difference between stateless and stateful. A stateless service is kind of like a basic calculator. You put numbers in, it spits out an answer, and then it totally forgets you ever existed. A stateful service, though, it remembers. It keeps track of stuff, usually by writing it down in a database. It has a memory. So why is everyone so wary of state? What's so dangerous about it? What is it about these components that wakes engineers up in a cold sweat at 3 in the morning? Because here's the problem. A stateless service? If it crashes, who cares? You just restart it. No harm, no foul. But your database, your state, if that gets messed up, you can't just reboot it. It's not that simple. You're in for some painful manual data surgery. And the whole time, your app is probably down for your users. And that is why we try to keep state contained, isolated, as much as we possibly can. All right, so let's look at the toolkit. What are the reliable, time-tested, and kind of boring components we can use to manage all this state and complexity? So, first up, the database. This is where your state lives, so getting this right is priority number 1. Your schema, the blueprint for your data, it needs to be something a human can actually read and understand. Then you've got indexes. You gotta add these to speed up the queries you run all the time. For queries themselves, let the database do the work. That's what it's good at. Use things like joins. Don't pull a million records into your app and try to stitch them together in a loop. And finally, a huge one, replicas. You make copies of your database just for reading data. That way, all those read requests don't slow down the main database that's busy writing new information. It's all about protecting that core. Okay, what about slow stuff? Like say a user uploads a huge video file. You don't want them sitting there staring at a spinner for 5 minutes. The pattern here is super simple and super effective. Step 1, do the absolute minimum amount of work you can, just enough to tell the user, yep, got it, we're on it. Step 2, you then push all the real work, the video processing, whatever, into a background job. The user gets a snappy response, and the heavy lifting happens behind the scenes. All right, let's talk about caching. This is a perfect example of the difference between a junior and senior engineer's mindset. A junior dev sees something slow, and their first instinct is, cache it, it'll be fast. Problem solved, right? But a senior engineer, they've seen things. They've been burned. They pause, and they ask, hold on, why is it slow? Because they know that a cache isn't free. It's another source of state. It's another place where you can serve old, stale data. It's another layer of complexity that can introduce the weirdest bugs you've ever seen. This next one is a really important distinction to get right. It's job queues versus event hubs. So a job queue is basically you giving a command. It's like pointing at someone and saying, you, go render this PDF. It's direct. An event hub is totally different. It's more like a public announcement. It's someone shouting, hey everyone, a new account was just created. It doesn't know who's listening, it doesn't care, it just broadcasts that something happened. These are very different tools, and you gotta know when to use which. Okay, so we've got our tools. Now let's talk strategy. How do we actually put this stuff to work in a real system? Because it's not just what tools you use, it's how you use them. When it comes to moving data around, you basically have two choices, push or pull. Pull is when your app constantly asks the server for updates. Think about refreshing your email inbox over and over. Anything new? How about now? Now? It's simple, but it can be really chatty and inefficient. Push is the opposite. The server does the work. When a new email comes in, the server pushes it to your phone. Boom, it just appears. It's more complex to set up, but way more efficient for real-time updates. Look, you can't optimize everything. You just can't. You have to pick your battles. And that's where the idea of hot paths comes in. Think of these as the major highways of your system. They're the parts that handle the most traffic, the most data, or are just the most critical to making your product work. And this is why these hot paths are so important. Think about it. A bug on the user settings page? Annoying, maybe, but not the end of the world. But a bug on a hot path, say the checkout process for an e-commerce site, that could take down the entire business. There are way fewer good solutions for these critical paths, and when they go wrong in a really spectacular way. This might be the most important part. A great system is not one that never fails. Let me say that again. A great system is not one that never fails. Because guess what? All systems fail, every single one. A truly great system is one that is designed for failure. It expects things to break, and it knows how to handle it gracefully when they do. So how do you actually plan for things going wrong? You build in what we call observability, the ability to see what's happening inside. That means aggressive logging, especially when things go wrong. You're going to need those logs to figure out what happened. It means watching the right metrics. Don't just look at the average response time. Look at the P95 or P99. The experience of your slowest 5% or 1% of users. That's where the pain is. And it means being smart about retries. If a payment request fails, you can't just send it again blindly. You might double charge someone. You use something called an idempotency key to make sure the system knows, hey, I've seen this transaction before, don't process it again. And this leads to a really critical decision you have to make for every part of your system. When something it depends on breaks, does it fail open or fail closed? Let's take an example. If your service that prevents too many requests, a rate limiter, goes down, you probably want to fail open. Just let all the traffic in. It's better than blocking legitimate users. But what if your authentication service goes down, the one that checks passwords? You absolutely 100% must fail closed. Block everyone. It is always better to deny a real user access than to accidentally let a bad guy in. Which brings us right back to where we started with this just perfect analogy. The author says, I'm not a plumber, but I imagine good plumbing is similar. If you're doing something too exciting, you're probably going to end up with crap all over yourself. And yeah, that's basically it. Good system design should be like good plumbing. It should be boring. The second it gets exciting, you know you're in trouble. So I'll leave you with this final question to chew on. Is the real goal here not to build something flashy and impressive that everyone talks about, but maybe to build something so stable, so reliable, so boringly effective that nobody ever has to think about it at all? Is the pinnacle of our work to become invisible? Thanks for joining this explainer.